Dr. Yuksel, hello. Can you hear us?
Hi, Andreas. Can you hear me? Hi, Andreas. Andreas, I cannot hear you.
Andres, we cannot hear you.
How about now? Can you guys hear me now?
Yes, yes, yes.
Yes. How are you doing, Serdar? Good to see you.
Good, Andreas. I apologize for being late.
No, you're fine. You're absolutely fine. So we'll wait to until in a couple of.
Andres, we cannot hear you.
Oh.
Let me just see if I can share my screen.
Oh, can you guys hear me now?
Yeah.
Yes. How are you doing, Serdar? Good to see you.
Good, Andreas. I apologize for being late.
No, you're fine. You're absolutely fine.
Andreas, are you able to see my slides?
Yes. And can you hear me also?
I can, yes, I can.
Okay, great. So I'm gonna go ahead and say, just a few words about the seminar, and then I will turn it to Nishant to introduce you.
Okay.
Thank you again for participating in our series. This is the inaugural series, so you are a special speaker for us today. And we have a very good turnaround. Several speakers have been subscribed already in the YouTube channel. That's very encouraging. So it's 12. Let's get started. Good afternoon, everyone. Welcome to the very first seminar of our new data-driven learning and control series. I'm thrilled to see such a great turnout and to kick off what promises to be an exciting platform for sharing the latest breakthroughs in data-driven systems. A special thank you to my students, Aditya Dave and Nishant Senthil Kumar, for their dedication in organizing this series. The hard work behind the scenes has made today possible. Remember, this is an interactive space, so feel free to engage with us through the live chat on our YouTube channel. And Nishant and Aditya will make sure to get your questions through the seminar series. Now I'll turn it to Nishant to introduce our speaker.
Hello, everyone. Thank you for showing up for our talk today. And I'm really honored to introduce today's speaker, Dr. Serdar Yuksel. He's a professor at the Mathematics and Statistics Department at the Queen's University. And his research interest broadly spans the fields of control theory, information theory, and probability. And he will talk more about what he's doing in his seminar today. But before that, just a short bio of Dr. Yuksel. He did his undergrad in Turkey at the Bilkent University, and he did his master's and his PhD at the University of Illinois Urbana-Champaign under Dr. Tamer Basar. And after which he did his postdoc at Yale, and then he joined Queen's University. And right now he's a professor at the Maths and Stats department. And he has held visiting positions at KTH, Royal Institute Sweden, and the Bilkent University. And right now he's also a senior editor at the Transactions and Automatic Control Journal. It's a really prestigious journal in the controls community. And his group and his work has contributed a lot in very prestigious journals in the control community. And recently, one of their works got a spotlight at the NeurIPS 2024. It's one of the best AI conferences in the world. And without further ado, I'll let Dr. Yuksel take over the talk.
Thank you very much, Nishant. Thank you, Andreas. Thank you for the invitation and for the organization. I'll now try to share my screen, and please let me know, Nishant, if everything is as planned.
Yes, we're good to go.
And Nishant, as a speaker, I won't be able to see if there are any questions. I'm happy to take on questions as we speak, or we can save them some of until after. But sometimes interactive discussions are more productive. So maybe you could be the moderator in case questions.
Yes, definitely, yes. I'll help you connect to them.
Thank you. Good afternoon, everyone. Good morning for those who are not in the Eastern time zone, I do not know who else is participating overseas. So good day, I should say. I'd like to thank Andreas for the invitation and for Aditya and Nisant for all the emails and for accommodating my time constraints. So thank you very much. And I think that hopefully there'll be a very beautiful and very fruitful, productive venue for us to exchange ideas. So for this talk, I will try to give in a sense, the first 10 minutes or so will be of a tutorial type. Because learning or approximations, they mean very different things to different people. I just want to set the stage for the analysis to come. And then hopefully the first 10-15 minutes should be accessible for the audience who is really not engaged with stochastic control, but hopefully may find some pathways to get into the field and to try to maybe think of different ways to ask questions and obtain solutions, especially for beginning graduate students. So this the title is very much self-descriptive: Robustness to Approximations, Learning and Incorrect Models in Stochastic Control. And this is a joint work with a number of my students. It has been basically a program that we have been working on for a number of years, starting from the PhD thesis of Naci Saldı and my colleague Tamas Linder, and then we have been working with my other colleagues, Ali Kara and Somat Pradhan, and Emre Demirci, Yichen Zhao, Zachary Selk, and Yanglei Song. And I will try to also highlight the specific results due to their collaborations. So a control model is described by the following. So I'll be discussing discrete time and also continuous time towards the end. And the continuous time discussion will be mainly with the understanding that once we know the theory in discrete time, once we know the approximation and learning results in discrete time, the extension to continuous time is really almost immediate. I'll try to give that message towards the end. But continuous time often comes with its own technical vocabulary, and sometimes it's a bit intimidating for a graduate student. So I'll just save that part towards the end. So a discrete time control Markov chain has the following form. So we have a f of xn, un, wn, and f is a function, and wn is an IID sequence. Without any loss, you can take it to be from the interval 0, 1. Here, xn is the state, un is the action, and this dynamics defines a conditional probability measure for the next state, given the current state and current action. Now, the design problem is to come up with the control action, un. So at every time stage, we need to select the action towards some criterion. For example, we may want to minimize some cost function, expected cost function, or sample path cost function. Or we might say, okay, I'm happy with some stabilization or some performance guarantees. But depending on the criterion, the goal is to design a selection of the UNs, given what we know. So the information structure is very important, because information structure tells us what can we do, in the sense that what is available to us, so that we can map what is available to us to what we can do. For example, we talk about admissible policies. These are policies where history is available to us. We can talk about Markov policies. These are policies where we can only look at the current state and the clock. And we can talk about stationary policies, where we can use the current state, but there's no clock. There's time invariant, in a way, lookup table. Now, this is for the case where we have fully observed Markov decision problems. And I'll briefly touch on the case where we have partially observed models and the multi-agent models. But as the introduction, I want to give this discussion first. Now, typically, though, we don't really know what F is. And typically, we don't really know what WN is. Almost every model we are given is an approximate model. And often, this raises a very important question that every design problem should really be embedded with robustness. So we have to be robust to unknown dynamics, unknown initialization, unknown driving noise, unknown models. Right? It's a classical problem. And in this talk, I'll try to present some results along this direction in a variety of uncertainties which characterize robustness. Now, typical cost criteria for such problems is you can have a finite horizon cost, you can have a discounted horizon cost, discounted infinite horizon cost, you can have an average cost problem, and you can have other criteria also, for example, cost up to an exit time, or sample path cost, for example, especially for average cost criteria, sometimes one talks about not just minimizing the expected average cost, but sample path average cost. And then you can talk about, as I mentioned earlier, maybe in some applications, such as in queuing theory, one just wants to make sure that the system is stable in some sense. And there are a variety of setups and characterizations of what one means by stochastic stability. Okay. So typically this umbrella problem, this big set of problems in one large umbrella is called Markov decision processes. They're Markov because the dynamics is control Markov in the sense I described earlier. And it's a decision process because we have to come up with the decisions for every UN. And it's a stochastic process. Okay. Now, the language to understand the rigorous study for such problems passes through probability measures. Because in the end, we have a stochastic flow characterizing the evolution given a policy. And especially when one talks about existence, optimization, approximation, and learning, it's very important that one provides a probability theoretic footing on the underlying probability space and various notions of what it means to be approximate. And for this, we'll characterize a number of notions of convergence. The most important one, the most common one is what we call V-convergence. So we say that a sequence of probability measures mu n on some space X, and this space is going to be taken to be what we call Borel space, standard Borel space. It basically means a Borel subset of a complete separable metric space. But if you have not really heard of this expression, please don't worry about it at all. Such a space behaves like the real space, or a countably infinite space, such as a space of integers, or a finite set. So in a sense, if you understand the theory for the real space, for the countably infinite space, or finite space, you can immediately generalize it to a Borel space. It's just that sometimes one has to work with specific properties which are not available in those spaces, but those are often technicalities. So, but please, if you have time, look up at Wikipedia to see what a Borel space means, what a Polish space means, and then you will see that they have basically the properties of being either behaving like the real space, or a countable infinite space, or a finite set. So on this space, we say a sequence of probability measures converges to a measure mu weakly if this integral, the integral of the expectation of g under mu n, goes to expectation of g under mu for all bounded continuous functions. We say that the sequence goes to mu n goes to mu setwise if in this expression, instead of g being continuous bounded, we take it to be measurable bounded. Equivalently, we ask that for every Borel set, mu n of b goes to mu of p. So in a sense, this is a pointwise convergence notion for all Borel sets. Total variation is when we have the setwise continuity, but in a uniform sense. We take the uniform convergence over all Borel sets, or uniform convergence over all measurable bounded functions. Total variation. And a very important notion is of convergence is what we call the transport distance, one of which is the Wasserstein 1 distance. In this case, we take the uniformity in the total variation convergence to be those which are Lipschitz, with Lipschitz norm given by supremum of g of x minus g of x prime d of x prime, and we want this to be less than or equal to 1. Now, these four properties, four notions of convergence are related, but also very much different. For example, if X is a space which behaves like, for example, the Euclidean space, meaning that it's a complete separable metric space, the set of probability measures under V-convergence is also a complete separable metric space. Under setwise convergence, it is not a metric space. We cannot define a metric which defines convergence. Under total variation, it is not a separable space. And under Wasserstein distance, again, it has the properties of the V-convergence. And you can, in fact, find different ways to metrize the V-convergence. When the space is compact, Wick and one Wasserstein convergences are equivalent. So there is a very rich theory behind these convergence notions, but it just also shows that defining different notions gives you a very different spaces of probability measures. And they're, in a way, representability and approximability properties. Now, given those definitions, we talk about a number of properties for transition kernels. So we say that the transition probability is setwise continuous in U, meaning that if UN goes to U, then the conditional probability kernel converges setwise for all X. So in our previous slide, we mentioned setwise continuity, setwise convergence of probability measures. What this says is that if un as un goes to u, the conditional probability will converge to the conditional probability given u. As an example, we have xk plus 1 equals f of xk uk plus wk. Now, in this case, if f is continuous in u, and if w has a probability measure which admits a density, and density is continuous and bounded, then this Markov kernel, control Markov kernel, satisfies continuity in actions in the setwise sense. A very important one is Wick-Feather continuity. In this case, we say that if xk uk pair goes to xu, then the conditional probabilities will converge weakly. As an example, suppose you have xk plus 1 equals f of xk uk wk with no restrictions on wk. In fact, wk may be absent. You may have a deterministic system. All you want is that f is continuous in x and u. So in this case, this dynamics defines a controlled Markov kernel, which is weakly continuous or Wick-Feather continuous. And this is a very important notion of continuity, which we'll be discussing later on in our presentation. Wasserstein regularity. So in this case, we require that the Wasserstein distance between, as you perturb your state, so you have x and y, the Wasserstein distance between the conditional probability measures is upper bounded by constant times the distance between the perturbed state variable. As you see here, there's a modulus of continuity. So K2 is a uniform modulus which controls how the deviation in the state affects the deviation in the conditional probability measure. As an example, suppose we have the following model: xk plus 1 equals f of xk, xt, ut, wt, and we require that f is Lipschitz in x and u for every fixed w. In this case, if you have Lipschitz continuity on f, this imposes the Lipschitz continuity, Wasserstein regularity in our transition kernels, where K2 is going to be the same as alpha. Now, why are these useful? If you are given a finite Poisson problem, and I'm sure many of you in the audience, you've been given a finite Poisson problem, then the way we solve it is through Bellman's equation. And often what is given to us is that you start with the terminal time, and then you go backwards in time. So Jn is equal to the terminal condition, and then Jt equals to minimum of C of xu plus the expectation of the value function of the next time state, and then you go backwards in time. Typically, if this admits a solution, then we conclude that the policy which achieves this pointwise minima for every time stage, say it is ft, achieves this minimum is attained by a function at every time stage where u is equal to f of x for the time stage. Then we say the policy is optimal, and the optimal cost is the cost given by J0 via backwards induction. But this is a condition for sufficiency. So it doesn't say when this is possible. It doesn't say, for example, when is it that the minimum is achieved, first of all, pointwise, and second of all, by a function f. And these are often known as measurable selection theorems. It says that, yes, this minimum exists pointwise, but can I realize it as a function which maps x to u? And the result is that basically, if under assumption S or W, Wick-Feather, there's a minimizing control policy. Under Wick-Feather assumption, the function, the value function is continuous. Under assumption Wasserstein regularity, it is Lipschitz. So under S, it's only measurable. Under Wick-Feather, it is continuous. Under Wasserstein, it is Lipschitz. So this will turn out to be very important for us when we talk about approximation and learning. Now, for the again, as part of the tutorial type discussion, many of you have also seen the discount cost problem. For discount cost problem, often one talks about the discount cost optimality equation. So this is given by the following operator equation. So TV of x is equal to the minimum on the right-hand side. So TV is going to be equal to V. And if under some conditions, for example, C doesn't have to be bounded, and there are some further assumptions that one could make. But in the most in the simplest setup, if C is bounded and continuous, then T defines a contraction map on the set of space of continuous and bounded functions under the supremum norm, and there's a fixed point, and the fixed point gives us a candidate policy which is optimal. And by a verification theorem, you conclude that under Wick-Feather condition, V is continuous. Under assumption S, it is measurable bounded, and under assumption Wasserstein regularity, it is Lipschitz under the condition. And finally, we have the average cost problem. For the average cost problem, this is slightly more technical, and there are three primary techniques for this problem. The first two build on arriving at what is known as the average cost optimality equation. So this is very similar to the discount cost optimality equation, but as you see, there is beta here. If you just put beta as 1 minus beta and take beta to 1, then you obtain the relationship between those two. And in fact, one major technique to solve these problems is to solve a discount cost problem, take beta to 1, and try to obtain a candidate solution which solves the equation. So those are known as basically the vanishing discount technique or the value iteration technique. And a very elegant technique due to Manne and Borkar is what you call the convex analytic technique, and it bypasses the typically what we call the geometric ergodicity or minorization condition. So the first two conditions, approaches, value iteration or vanishing discount technique, require typically a minorization type conditions. We can relax some of them, or Wasserstein continuity condition. However, for the convex analytic technique, you don't need those conditions. You only need the weak continuity and the compactness condition. However, you suffer from the fact that your optimal solution may not be defined for all state values. It may be restricted to a local subset of the state space. Now, we won't be talking about this today, but there are what makes stochastic control very rich, very interesting, and really very beautiful as a research subject is that information structure can be very rich, and the intuition we acquire from finite fully observed models really carries over to more general setups with lots of richness, especially when you go from partially observed models to multi-agent models to stochastic games, which we will not be discussing today. In a partially observed model, you don't see the state, you see measurements. But there's a standard technique where the standard technique is that you lift the problem to a problem where the partially observed model is reduced to a fully observable model, where the state is replaced by the set of probability measures or the set of conditional probability measures on the state. And then in a way, you have an uncountable space, Polish space, MDP, even in the simplest case where the hidden state is finite. And when you go to multiple agents, again, the problem becomes very, very interesting, but also very challenging, because in this case, standard techniques do not apply, but one has to really creatively come up with methods to solve such problems. But we will not be talking about this today. Now, so the summary so far showed the following. We have a very rich toolbox, mathematical toolbox, thanks to very prominent, very prolific researchers since the 1950s who studied all these problems in a wide variety of setups in continuous time, in discrete time, in very general spaces. However, computing them numerically has always been difficult, and it has been even, there are papers which are still written in this very day, because it's a very, very challenging problem to come up with rigorous methods with performance guarantees. And often, even when we have computational methods, we often, as I mentioned at the beginning of the talk, we don't really have a model, or we don't have access to the true model or the true dynamics of a given system. An engineer or an operations researcher or an applied mathematician is typically given an approximate model, and we have to work with the approximate model. And our model is typically shaped by physical principles or some data, but they are bound to give us approximations. So in our presentation, what we'll do is we'll try to give a unified perspective for both approximations and robustness in both discrete time and continuous time, and then we'll talk about some implications for learning in the spirit of this seminar series. Now, approximations. So before I proceed, if there are any questions, I'm happy to answer. So in the first part,
I don't see questions so far.
So in the first part, we'll talk about approximations, and here's the strategy. So first, we'll approximate the action space with a finite set of actions. So in a way, our action set is typically a large action set. If you assume it to be compact, the first aspect will be the first approach will be to verify that we can, without any loss, approximate our action set to a finite set. And then we'll try to approximate the state space also. And together, these two, finite action set and finite state set, will define a finite MDP. We'll obtain a solution for a finite MDP, apply to the true model, and we'll try to show that, yes, in fact, this is with very little loss as we play with our granularity of our state space and action space. And then we can solve, for example, what we learn in a basic MDP class on optimization. Now, a function is called a quantizer if when we map a larger space to a smaller space. In particular, we can define a quantizer policy, a stationary quantizer policy, if we have a finite set U, and we map our state space to a finite set U. So we call this stationary quantizer policies. If basically Q of X, basically this is the image of X under the map Q. If it is finite, we have a quantizer. And if you have a map which maps the state to this quantized state space, then we'll be having a stationary quantizer policy. Now, remember our optimality equation, discount cost optimality equation. If U is compact, we know that for every n, we can find a nested sequence of subsets of U such that for every A, the minimum over the finite set can be designed in such a way that the diameter of each approximation is at most 1 over n. This is by the compactness of my state space. Because you can cover the compact set with balls of radius 1 over n. And we can then define a contraction operator for the discount cost optimality for this finite set by minimizing over the finite set and not the original action set. And then we can reason that as we increase n, as we make our sequence of finite subsets finer and finer, for every fixed U, this map is going to be monotonically non-increasing, it's going to be monotonically non-increasing. And with that in mind, then we have the following first result, saying that under the Wick-Feather condition, we can find a finite set of actions such that we are with arbitrarily small approximation error. Meaning that the solution of the finite approximation set, finite action set, applied to the true MDP is at most epsilon, away from the optimal solution. And just to give you the line of reasoning, I won't give you too many theorems, but I just want the beginning graduate student to see what's the approach for such problems. And typically, you work with the optimality equation. And another technique will be to work with the induced probability measure. And I'll be talking about this later on. And I'll try to say, we make the point that there are really two paradigms for such problems. One, you perturb the optimality equation, and in the other one, you perturb the probabilistic flow. And sometimes they go hand in hand. Sometimes one is more suitable for analysis than the other one. Because you subtract the fixed points from one another. The first fixed point is TNUN, the other one is TU, and then you add and subtract, and then subtract. You use contraction here, use approximation here, put this on the other side, and then you are able to show that if you put this on the other side, you have 1 over 1 minus B, and if TNU goes to TU, by the conditions given, we conclude that UN goes to U. And likewise, for the average cost, the same applies, but we just need the average cost of the optimality equation to hold. So this was the relatively easy part. The difficult part is to, okay, so this was for the Wick-Feather continuity. The same also applies for setwise continuity. Remember, setwise continuity was a continuity notion where the transition kernel was only continuous in the actions, but strongly in that sense. It's a complementary condition. There are many examples where the MDP is not weakly continuous, but it's setwise continuous in actions only. So once again, you have the same result. You can approximate a compact action set with a finite action set with arbitrarily small loss, and likewise for average cost also. For average cost, again, we need some conditions, and typically they amount to some compactness conditions on the set of probability measures, which are invariant measures of my Markov process under any stationary control policy. Okay. So again, the reasoning is that you apply value iteration for discount cost, and for average cost, here you apply the convex analytic technique, and there's a very beautiful result which is very much used in this type of analysis by Serfoso or Langen, which says that sometimes when you converge, have an integral, if the measure also converges and your cost function also converges, sometimes weak convergence is sufficient. But for that, you need the condition that Cx pi x and Cx pi, they converge in a continuous manner. And if nu goes to nu setwise, then pointwise convergence is sufficient. So because sometimes it's very important to I think know that you can go beyond the classical notions of convergence that we learned, for example, in a measure theory class. Say, for example, dominated convergence theorem or monotone convergence theorem. You are able to also perturb simultaneously both the measure and the integrand. Now, so far we discussed the action space quantization, but the more interesting, the more challenging question is, how do you approximate the state space? So this was studied in Naci Saldız's PhD thesis. There were many other studies in 1980s, 1990s, and typically those studies imposed strong Lipschitz conditions. And the primary contribution of this paper is to show that even for under weak convergence, one could obtain rigorous convergence guarantees. So let once again X be a compact set. In this case, we can again cover the compact set with balls of radius 1/m for any m. And then we can talk about the nearest neighborhood map, which assigns every state in my state space to the nearest element in my finite approximation to that point. And then this defines a partition, a quantizer for the state space. And given a partition, what we do is the following now. We'll obtain an approximate model. Now, given a measure psi, this measure is going to be defining a weighting average in the following sense. So what I'll do is I'm going to obtain a finite approximation. So Zm is the representative agent for the bin, the ith bin in my approximation. And for my cost function, I take the average of all the other states, and I take their weighted average given the measure psi. Now I keep this psi as a design parameter because later on we will see that sometimes we can design this, but when it comes to learning, we cannot design this. This often comes from the exploration policy, which sometimes cannot really be designed. And the approximate transition kernel is going to be, again, you take the average of all the states in the bin, and then you take the push forward of the image under the quantizer map, meaning that, so Qm star P is going to be equal to probability of the image being in the partition corresponding to the bin J. So I'm going from I to J, the bin J. So I'm going from bin I to bin J. I'm taking the average with the weighting average, psi, and I'm taking the image, also quantizing them. So what this does is that this defines a finite MDP now, because I have an approximate cost function, approximate transition kernel. Everything is finite now. And the result is that if under the Wick-Feather regularity, remember Wick-Feather regularity was saying the following, my cost function is continuous and bounded, and my transition probability is weakly continuous, and this action space is compact, then for any discounted cost problem, the solution of the finite approximation applied to the true model is asymptotically near optimal. Asymptotically optimal as you increase the granularity of the quantizer. And the same applies for average cost. Here we just require, again, some minorization conditions. And in this case, so the original result is due to Serdar Linder and our paper in 17. And the refinement where we don't need to have total variation, it suffices to have a Wick-Feather property, was done by a paper by Ali. It seems there's a question.
No, sorry, I pressed a hand by chance. Sorry.
Now, with Wasserstein regularity, we can obtain a further structure. In this case, suppose that we have a maximal diameter. You can show that under Wasserstein regularity. Again, this was on Nali Salda's PhD thesis. You can obtain a uniformity bound and control the perturbation error with the diameter in your approximation. But anyway, Wasserstein regularity allows you to obtain a relative convergence also, which you don't have under the Wick-Feather property. And likewise, for average cost, you can also obtain a similar uniformity condition. For the Wasserstein regularity, we need both minorization and also remember this K2, which is our regularity condition for our Wasserstein transitions. If this is less than 1, and then we have minorization, then again, we obtain the following. Give me the finite model, solve the average cost problem, apply to the original continuous space MDP. The error is uniformly bounded by some constant times the diameter of your quantized action space. Extensions, you can extend this to unbounded spaces. For example, if you have a non-compact state space, often what you do is you apply Lyapunov theory to approximate the non-compact space to a compact space. You can obtain rates of convergence, as I mentioned, under explicit bounds. And you can, in fact, you can also show under some conditions the order optimality of the approximation using information theoretic arguments. You can apply non-uniform quantization. For many applications, if your state space is especially not compact, you may want to apply non-uniform quantization and you can obtain explicit bounds. You can apply these results to partially observed MDPs, because pure MDPs are going to be reduced to belief MDPs. And if you can show, for example, that belief MDP is Wasserstein continuous, a result due to Emre Demirci and Ali Kara, then you can apply the theory for those problems and you can obtain existence and application results also for partially observed macro decision processes for both discounted cost and infinite average cost criteria. And finally, we can also apply the same in Nagi's thesis and his book. There are also results for the multi-agent case setups using the same principles, but without dynamic programming ideas. Because all these discussions here, they give a recipe on what to apply. Even though we cannot apply automatically all the techniques, the machinery is still applicable. Now, so far we talk about the discrete time approximation, so the quantized approximations, which is one way of robustness, because I have a continuous space model, I'm approximating it. But I have a design, I'm designing my approximation. But for many applications, the approximation is not subject to design. We are given an approximation, and we just know it may not be the true one, and we want to be confident that our solution is going to be performing sufficiently well. So for this, I'm going to give a setup where we have a partial observed model. So again, T is our kernel, and suppose that we have our measurement kernel given by yt equals g of x t vt. And in this case, say the depiction. So I have my prior is p. So x0 is given with a initial randomness, where the randomness has measured p. And then so from p we have x, and then x is subjected to a measurement channel. The measurement channel gives us the measurement value y, and the controller can only see y to come up with an action. You only have access to past measurements and past actions and the current measurement. And we can have a problem where, for the sake of presentation today, the discount cost criterion, but we can apply the same machinery, same analysis for average cost criteria also. So the average problem was also studied. Now, then what is the problem? So once we state the problem, hopefully it will make a lot of sense for the audience. So suppose that we have a sequence of probability measures. So Tn, Pn, Cn. So Tn is my transition kernel, Cn is my set of cost functions, Pn is a set of priors. And suppose that this Pn, Tn, Cn go to P, T, C. But the important one really is Tn and T.
Sorry, Dr. Yuksel, there's a question. Sorry to interrupt you. May I ask you?
Yes.
So the question is about from Andreas, and it's what's the implication of applying such approximations in non-classical information structures?
Right. So this allows you, for example, you can show that you can obtain a numerical solution to Wissenschaft's problem, and you can show that Wissenschaft's problem can be rigorously approximated using finite approximations. But Wissenschaft's problem is such a difficult problem that you will need a very strong computer. But what it does is that, for example, there were a lot of studies, numerical studies, on Wissenschaft's counterexample. But those studies were not supplemented by a rigorous theory which says that if you keep doing this, if you keep increasing your refinement, you are guaranteed to solve the problem. You're guaranteed to approximate the problem. So all the numerical approaches, for example, we're saying that okay, we are within an epsilon of the previous best known bound, right? So this results, for example, in fact, Nagi's thesis and a paper we wrote afterwards showed that you can rigorously show that quantized approximations are guaranteed to converge to Wissenschaft's solution as n goes to infinity. But the price you pay is that it's an asymptotic result. So in a way, you can obtain rigorous techniques to solve problems.
And I also have a question. So when it comes to using approximations for large systems, let's say in the learning setting, like machine learning setting.
Right.
So some components of the state, let's say it's a vector space state, and some components of the state might influence or might have influence on the evolution more than the others. So is there a notion that could be added on to this to capture let's say some state has a particular level of conditional the way in which it affects the distribution, could an approximation in that particular component of the vector space lead to let's say asymptotic or some sort of convergence gap?
So let's save this for afterwards, because it's a very good question. Because for that, I think you are pointing out to a very important question on non-uniform quantization. Because you are saying that can we design a better quantizer than a uniform quantizer? And absolutely, you're definitely correct. But let's save this question for after the. Okay. It's a very, very important question.
Thank you.
So in a sense, the robustness question is the following. So given a model Tn and a true model T and approximate model Tn, suppose that, I apologize for this typo here. Suppose Tn goes to T, Pn goes to P, and Cn goes to C. Is it the case that the value function is continuous? But the important engineering question is that, suppose that I'm given Pn, Tn, Cn. I design a policy for Pn, Tn, Cn. I apply it to I design gamma star n, assuming that what I'm given is the true one. I apply to the true model. Is it the case that this value, the achieved cost under the incorrect optimized model, does it approach to the true cost as n goes to infinity? And again, in the spirit of today's seminar series, empirical consistency of data-driven control. Suppose I'm learning my model through empirical data. What can I say about consistency in the sense that if I learn my gamma star n using empirical data, is it the case that when I apply to the true system, do I have asymptotic convergence? So I will not talk about robustness to incorrect priors. That is a problem of its own. So it requires different techniques. So I will not be talking about that, but I'll be talking about the robustness in the kernel. But the problem is I think very important to in a way digest. So far we discussed the case where Tn was a quantized approximation of T. But here I have no control over how it is approximated. There's no monotonicity. All I know is that Tn is an approximation of T. This is a classical problem, as I mentioned earlier. Every control system has to be robust. And there are so many different techniques on robustness in discrete time, continuous time, deterministic and stochastic systems. Right? Very, very different techniques, very beautiful creative arguments. And we are focusing on a particular type of robustness in our discussion, as I discussed earlier. So once again, we talk about the notions of convergences because this is going to be universal in our analysis here. We talk about V convergence, right? Wasserstein convergence, setwise convergence, total variation convergence. We can talk about pointwise convergence, or we can talk about uniform convergence, and we also can talk about what we call continuous in-state convergence, which means the following. So in this version here, as you see, Tn goes to T pointwise. Here, Tn goes to T jointly as Xn also goes to X. And this turns out to be critical. In fact, you can show that this alone is not enough, but when you have this is sufficient. So for those of you who have some insight, you can recognize that this condition is, in a way, gives us some equicontinuity condition. And this is often what makes V convergence to be sufficient. In the absence of equicontinuity, the results are not going to be sufficient for convergence. So let's just give very quickly some examples just to motivate. For example, suppose this is my true model. And suppose I have some sequence of approximate models. So say f is continuous and I have a polynomial approximation. And I know fn goes to f pointwise. In this case, you can show that your models will converge pointwise. And when they converge pointwise, then you have V continuity, V convergence. Suppose you have the following model. So in classical robust control framework, you have f tilde is equal to f plus some perturbation of the system. And suppose as delta goes to 0, the model approaches the true model. So in this case, again, we have V convergence, but we do not have total variation convergence because the Dirac delta functions, as they converge, their total variation distance is always going to be 2 because the mass is always completely not aligned, but V convergence holds. So suppose that we have the following model, say f of x u w is equal to f of x u plus w. And suppose we know f, but we don't know w. Now this is important for learning, for sample complexity and empirical learning. So suppose I know what f is, but I don't know what wt is. In this case, if I know that wt is estimated by mu n, if mu n goes to mu weakly, then you can show that the kernels also converge weakly. Therefore, if I can obtain a robustness result for V convergence, I can ensure that my system is going to be empirically consistent. So in particular, if mu n goes to mu weakly, then the transition kernels also converge weakly. If mu n goes to mu setwise, the transition kernels converge setwise. If mu n goes to mu in total variation, the transition kernels converge in total variation. If mu n goes to mu in the Wasserstein distance, then Tn also goes to T in the Wasserstein distance. So therefore, learning in the noise model manifests itself also in the learning of the kernel. And likewise, for example, you can also go further. Suppose that you know that mu n goes to mu weakly, then what jointly fn and f, they simultaneously change. Once again, even if they both change. Both mu n changes and f changes. If fn goes to f pointwise and mu n goes to mu weakly, we again can establish convergence. So these last two ones are very important, as I'll be discussing later on. Now the summary of the results is as follows. If we only have continuity and robustness under total variation convergence, we cannot have robustness and continuity, as I discussed earlier. But if we have, let me just focus on the case with fully observed case. So continuity and robustness do not hold even under total variation convergence. But if you have continuous convergence in the sense I discussed earlier, meaning that as xn goes to x and un goes to u, I want the kernel, conditional kernel, to change simultaneously, then we have robustness and continuity. And under set-wise continuous convergence, we again have continuity and robustness. And likewise, if you have continuous convergence under total variation, once again, we have continuity and robustness, with also a modulus of continuity. With convergence, we don't have a modulus of continuity, but with total variation convergence, as well as with Wasserstein continuous, we also have a modulus of continuity, which means that I can give a rate of convergence. So in particular, and there have been some recent studies on this. In this case, basically, if you have Lipschitz regularity in the value function, and you can build on that by relate the transition of the kernels and to the acquired value function and their robustness properties. And likewise for average cost also, studied in Ich and Zhou's master thesis. Now, the application to data-driven control. So in this case,
may I ask a question?
yes.
Yeah. So like I've seen some notions where like in a learning setting, when people try to learn models, they use these Hofting, union bounds, and Bernstein inequalities to bound how close your any strategy that's derived based on your learned model versus the true model. So I mean, looking at these notions, they seem more rigorous to when compared to the Hofting and union and all of these things. Like, what's your take on that?
I think there's definitely value in both approaches, and they are in fact very related. But listen, let's save it for after the seminar, because
Okay.
Sorry, stressed out with only 15 minutes left. But what I want to discuss is afterwards. It's a very good question, and so suppose that we don't know the model, and we don't know the noise distributions, and suppose that we are trying to learn the noise distribution using empirical estimates, right? So suppose xi comes from an IID sequence, and I compute the empirical average for xi, and I'm trying to learn mu n. Now, what we know is that mu n goes to mu for every Borel set B by the strong law of large numbers. So every beginning graduate student has seen this, right? Now, if this holds for every fixed B, it will also hold for 2 of them, for 3 of them, for 4 of them. Because a set of measure 1, if you take the intersection of finitely many sets of measure 1, the intersection will also have measure 1. In fact, if you take the intersection of countably many sets of measure 1, the set will have again measure 1. So therefore, the same reasoning applies for a countable collection of functions, but not for an uncountable collection of functions. Therefore, mu n goes to mu weakly, because weak convergence is characterized by a countable collection of convergences, but by the denseness of polynomials, for example, in the set of continuous bounded functions. So hopefully the beginning graduate students can reflect on this discussion. So therefore, mu n goes to mu weakly, and also in Wasserstein distance, but mu n does not go to mu in total variation. So therefore, all the discussions I discussed earlier show the power of the preceding theorems in a learning context, because in a learning context, we can really only hope for weak convergence or Wasserstein convergence in general, unless we have some stronger a priori assumptions, such as kernel density estimations. So there are some applications for this for data-driven learning, but I will skip these discussions because I really mentioned in a way the essence of the argument there. So the point is that if I converge, if my estimate for the model driving noise converges weakly, the kernel converges weakly, then all the empirical consistency results becomes the corollary of the analysis, and likewise for the Wasserstein regularity also. The second application is on reinforcement learning. So many of you know about Q-learning. So Q-learning algorithm is a very powerful algorithm. It's given by the following very simple to execute update equation. And you have a square summability condition, but not summability condition. And if you run your algorithm, then you know that as n goes to infinity, Qn or Qk will go to Q star, but Q star is going to give me my optimal cost and also my optimal policy. The action attaining this minimum is going to be my action, and that defines the stationary policy. However, this is only applicable for finite MDPs and not continuous MDPs. So what can we do about that? So the idea is that this was in our recent several papers, quantize the state space and pretend that your quantized state space is the actual state space. So in a way, quantize your rho, run the Q-learning algorithm, and what you can show is that this quantized model, with the price that the exploration policy cannot be arbitrary, it has to induce an ergodic process. In particular, it can be, for example, a Harris-Recurrent Markov chain, for example, in this example. Then this will converge to a limit, and the limit is going to be the optimality equation of a finite MDP exactly as defined earlier, with a weighting measure characterized by the invariant measure of the exploration policy. So in that sense, this discussion becomes a corollary of the very first result I mentioned earlier on the finite state approximation. So even though the quantized model is no longer Markovian, you can still apply some argumentation to show that the Q-learning converges. In fact, the convergence of Q-learning was already shown by Sink and Jordan and their collaborators in earlier in 1990s, but they had not shown what the limit was. And in Ali Kara's work, first for PMDPs and then with Nadi Saldi, we show that the limiting equation in fact solves an approximate MDP, and the approximate MDP is given exactly by the weighting average as given earlier. Thereby, combined with the previous results, you can establish the near optimality of the approximate MDP. So therefore, you can apply Q-learning even when your space is continuous. And in fact, you can obtain further refinements when you don't have the Harris recurrence condition for your induced Markov chain under the exploration policy. Unique ergodicity is sufficient, but with some refinements. Now, okay, so then this part concludes the discrete time theory, and that was going to be the bulk of my presentation, but I also want to touch on the continuous time briefly, because I know often when one learns this subject, there's a big gap between discrete time and continuous time. And the point I want to make is that the gap really shouldn't be as large as it is perceived to be. So in particular, for a continuous time process, what often one talks about is that you have a state process, and you have a drift term, and you have a diffusion term. And typically for the continuous time systems, the noise has a particular form. So the WT is the Brownian noise. The Brownian noise, you can think of it as the limit of the normalized random walks, where basically you have a Gaussian density with impulsive covariance matrices. You know, another way to motivate the Dirac delta function that all of us are very familiar with. So you can also think of a continuous time process as a limit of a discrete time process given by the following. So you in a way discretize this, you put h, but what you do is you put a root h here. But because you do root h here, when you apply the classical approximation divided by h, what happens is root h over h does not go to 0. That's why when you approximate this, you have a second term. And this gives rise to what is known as the Ito calculus. But the main reason is because of the root h term. So then you typically have some conditions, again, technicality conditions, often which I think what deters many to stay away from the continuous time theory. So you have some conditions to ensure that you have what you call a strong solution, which means that the path is a function of the noise. And then we define a set of admissible policies. We want the policies to be such that they are independent of the feature of the driving noise. And again, from this discussion onwards, everything becomes very parallel, very similar to the discrete time case. We talk about Markov policies, which only depend on the current state and the clock. Stationary policies, which only depend on the current state and does not depend on the time. And then we have a discount cost criterion, and we talk about an optimality of this problem. And if it is attained, we say have an optimal policy. And a very beautiful, very strong existence result is due to this reference by Arya Apostatis and Myrna Ghosh and Vivek Borkar. Then under those assumptions, there's an optimal solution, and the optimal solution has some regularity properties, bounded and twice continuously differentiable. Again, but the same problem, we have existence. Can we approximate? This is the question. So we have an existence, and the same optimality equations also apply for average cost, for finite rising cost, for cost up to an exit time under different criteria. So can we approximate the optimal policies? For example, can we show that piecewise constant policies are optimal, Lipschitz policies are optimal? Can we apply time discretization? Can we show that in a way we can obtain a discrete time approximation, solve it, and apply it to the continuous time problem? Are we near optimal? So these are all connected problems, and the discrete time approximation problem is a classical problem studied by Kushner and Krylov and many others. And the robustness problem is relatively recent, with some references. And so in a sense, the robustness problem is the following. Suppose this is my approximate model. So Bn is my approximate drift, sigma n is my approximate diffusion matrix. If sigma n goes to sigma, and if my cost function approaches C and my Bn goes to B, can I say that I have the same robustness properties? Okay. The same problem, but just with the continuous time language. And the result is that yes, we have that the value functions converge, and the solution of the incorrect model applied to the true model also converges when it's applied regarding the obtained cost function. And here the same spirit, you write down the value function that you obtain by the approximate, the optimal solution to the true solution, the true optimal problem when you knew the model. You apply triangle inequality. We just imitate the discrete time theory. In fact, the proof we were just following almost line by line the same machinery, but lots of additional analysis as you see for continuous time. You need to go into some functional analysis terms, but nonetheless, the spirit is really the same. And then a very important problem is the Brownian idealization. In continuous time theory, for example, we always see the Brownian noise running the system. But as engineers, many of us, we know that the Brownian noise is really, it doesn't exist. Everything's an approximation. No noise in the physical world has infinite bandwidth, right? So then the question is, what if I approximate the Brownian noise with some other approximation? For example, you can talk about finite truncations of the Fourier expansions. You can talk about what is known as the Wong-Zakai approximations, fractional Brownian approximations, and so on and so forth. So the result is that if you apply a Lipschitz policy, then you can show that your solution is going to be robust to the Brownian approximation. And finally, the last set of results will involve a near optimality of Lipschitz and piecewise constant policies. For example, the question is, can we approximate a policy with a Lipschitz policy without any loss or with arbitrarily small loss, or a piecewise constant policy? And the answer is yes. And here the paradigm is the following. We invoke a very interesting topology due to Vivek Borkar. So Vivek Borkar places a topology on control policies as follows. He says that Vn goes to Vu in his topology if this integral converges to this integral for every f which is integrable and which is square integrable, and for every g which is continuous in both state and action. In fact, this is related to what we call Young topologies in the more classical literature. And you can show that the value function is continuous in Borkar's topology. And you can also show that the space of continuous functions are dense in the space of all functions. Therefore, continuous functions are near optimal. Lipschitz functions are near optimal. Quantized functions are near optimal. And the very final result is going to be on discrete time approximations. You can, again, using a somewhat different technique, you can show that if you are given a continuous time model, you can obtain a discrete time approximation. You can solve the discrete time model, apply it to the true model, and you can show that the optimal value of the discrete time approximation converges to the optimal value of the original continuous model. Moreover, for every epsilon, the solution of the discrete time model, when applied to the true model, is going to be asymptotically optimal as h goes to 0. This applies to both fully observable case, partially observable case, and even the multi-agent case. Even the multi-agent case. And the proof, again, uses ideas from the perturbation of the flow of the equation. So in summary, I just want to spend a few minutes on the summary and see if there are any questions. So in this talk, what we did is we give in both discrete time and continuous time, we try to give a unified perspective on robustness and approximations. In particular, the techniques were either perturbing the optimality equation or perturbing the strategic measure or the solution measure given a policy. And often one calls this the weak convergence technique. In discrete time, we show asymptotic optimality of quantized control policies in both state and actions for both discount and average costs. And the conditions, in a way, one could argue that they are, in a way, complete conditions, in the sense that whenever we have an existence result, we have an approximation result. Then we talk about robustness with a more general perspective, where we don't perturb our own. The perturbation is given externally. We don't design our approximate model. But then we apply this to both data-driven learning. For example, we apply this to make sample complexity results when we are empirically learning the model. Or we discuss this to quantized Q-learning, because we apply Q-learning to a quantized model. And then we extend the same analysis to continuous time. And once again, we have the same paradigm. We are either perturbing the optimality equation, or we are perturbing the probabilistic flow. And we, in fact, saw that they're complementary. For example, perturbing the solution requires some function analytic techniques. Well, Somnath is an expert on PD theory, and with his machinery, we were able to obtain some of the results. With the convergence, we use more probabilistic techniques, and they often are complementary. And then we finally show that under general information structures for both discrete time, for fully observed, partially observed multi-agent systems, we can approximate a continuous time model with a discrete time model, which we know by now quite well how to solve. And we can apply them to the continuous model and obtain near optimal solutions. And the same also applies in a current ongoing work with Somnath Pratham. We're applying this to the average infinite horizon problems also. So with this, I conclude my talk in 58 minutes. Thank you.
Thank you so much, Dr. Yuksel. Thank you for the talk. And now we can take questions from the audience if they have any questions. Before the audience can ask, maybe I can start with my questions. So yeah, I had two questions, as you might remember. So the first one was, like, when there is a situation where like some components of a state, let's say the state space is a vector space, and some components of a state influence the evolutions or the cost or some parts of the MDPs more than the other. And is there a way to like work out the degree of influence into our approximations, and how well our approximation, or like how loose can we be with the approximations in a sense? Yeah.
I think it's a very good question. Now, in optimal quantization theory, for example, if you have a Gaussian density, if you want to approximate the Gaussian density, say with 4 bins, with 2 bits, you want to represent 2 bits to approximate the Gaussian random variable, right? If you apply, for example, there's an optimal solution, it's given by Lloyd-Max algorithm, because it's a log concave density. There's a unique solution if you run the algorithm. The optimal solution is going to be, you will be closer to the origin, a finer bin width size. As you increase the number of bins, in fact, you get closer and closer. You give more value to the more likely state values, right? In fact, you can show that as n goes to infinity, uniform quantizers are asymptotically optimal, but for finite n, you gain a lot by applying non-uniform quantization. So now you can apply the same intuition in this setup. The problem is that in this setup, when you apply quantized approximation, there's really no closed form. Because you see, the quantization manifests itself in 2 ways. In fact, one of my students is working on this problem. It manifests itself through the invariant measure, which is used to obtain the approximate model. And it's also used to obtain the width itself. Anyway, it affects itself both in the weighting measure and also in the expected error also. And these lead to a very non-convex problem, highly non-trivial problem. But the intuition is there, certainly. The intuition is that non-uniform quantization is better than uniform quantization in general.
Okay, thank you. And my second question was about these like Hoofding and union bounds that the people in RL community seem to use a lot. I've seen them do it for discrete sets and have a covering argument for, let's say, a continuous set in a sense. But like, what's your take on these kind of approaches, and how you, like, when compared to your things that you
So I think the approaches are, I mean, I don't know the specific paper you are referring to, but I can imagine where they're using that argument. They're probably using that argument to obtain sample complexity bounds.
Yes, yes.
The sample complexity bounds will, for example, if you apply this machinery also to obtain sample complexity bounds, you'll have to do the same things. For example, we know that, for example, the Wasserstein distance converges to 0. People, have studied all kinds of notions of convergence. For example, depending on the moment of the underlying unknown distribution. So then you can apply them. So my guess is that our colleagues who are doing that machinery, they're just doing it from scratch. They're obtaining bounds, but one really needs to see the precise statement to see the connection. But I can see what the motivation is.
Okay.
We'll have to do the same thing. What I mean is that we'll have to do the same thing to obtain, because now we show that the convergence is the same as convergence in the noise. Right?
Yeah.
And to show how fast I converge, we just apply the result. Osmo-Hoeffding inequality, or different types of things.
Thank you.
I have a question. Hello, Dr. Yuksel. Thank you so much for your wonderful presentation. My question builds upon a previous question that you had about non-classical information structures. All this talk about approximating models got me thinking along the lines of, do you have any insights on what happens if we change the information structure of a problem, like we assume an incorrect information structure, and could any of these techniques help bound the error that arises from that particular sort of incorrect assumption?
Right. So it is a very, very good question, very important question. So, yes, if you are given a given information, for example, our first paper on this subject was with Professor Tamas Linder, where we studied continuity for a PMDP in the measurement channels. So you perturb the measurement channel. How does the optimal cost change as you perturb the measurement channels? And our result was that if you perturb your measurement channels weakly, you are not robust, which means that no matter how close you are under weak convergence, there's an epsilon where that epsilon is stubborn. You cannot get below epsilon. However, if you are approaching in total variation, then yes, you are both continuous and robust, meaning that the solution that you apply for the approximate model to the true model converges to the solution of the true model. So in a sense, that total variation is a very strong notion of convergence, but it's always, when it's about information structures, you can show robustness. And you can show by counterexample that weak convergence is not strong enough. So often it is a very recurring theme. Therefore, it's very surprising when weak convergence is good enough.
I see.
So for MDPs, due to the optimality equation, due to the fact that there is some self-correction happening in the system, either through the contraction argument in the value, you are able to get away with weak convergence. But when you go into a general information structure, so and in fact also in our books with Professor Bashar, we gave a very extensive review of results of that type for both stochastic single agent problems, stochastic teams, and stochastic games, where you can show that you are not continuous under weak convergence. You are not continuous under self convergence. For stochastic teams and single agent problems, you are continuous in total variation convergence. And for stochastic games, you are not even continuous in total variation. So except for zero-sum games. So in a way, there are some results out there already, but there are still several open questions, and we can discuss them more some other time. But yeah, there are many interesting open questions, but there's a very large body of work. I mean, also in the economics community, this has been well studied, especially for static problems, especially, for example, epsilon Nash equilibria, for example. Is there an epsilon Nash equilibrium solution for a single agent game problem, for a single shot game problem, for a multi-stage game problem? So this problem of regularity properties in the information structure is a very interesting problem. There are many results already existing, but there are also many open questions.
Thank you so much for your detailed answer. It was very helpful.
I don't think we have any more questions from audience. Hello. Yeah, Dr. Yuksel, I can direct them to your email if they have any further questions. Definitely.
Of course.
Yeah, so far I haven't seen any more questions. Yeah, it was a pleasure having you talk at our seminar series.
Thank you, Nisan. Thanks very much. Thank you, Aditya. And thank you, Andres. Thanks very much. And hopefully we'll be in touch. Thank you very much.
Yes, definitely. Yeah, thank you so much.
Thanks a lot.
No.